Okay, today we have lecture number 15 of Fluid Mechanics 2 course. ME314 is the course code, and today's topic is potential flow. We are going to start, and we will talk about the velocity potential functions. In the earlier lectures, we have the kinematics of the flow, in which we have talked about the transformations, velocity fields, and rotational and irrotational flow aspect, and the idea of the stream function was invented. Today, formally, the lecture content goes with first we will define this velocity potential function, just like as we have done it for stream function. Then we will talk about what we call it a potential flow is an idealized flow, and it has certain features, and that flow is actually called as potential flow. We will look into the link between the relationship that exists between the stream function and the velocity potential function. So phi is a letter we use to represent velocity potential functions, and psi is a letter, Greek letter we have used, psi is a Greek letter we have used for representing stream function. Phi is for velocity potential function. Then the concept of flow net would emerge because these two functions representing family of curves, and these family of curves, how they are linked together is represented in one form. We call it a flow net, and it is quite a useful description of the flow, where we have idea about how the fluid is flowing. And then we will look into this velocity potential functions in cylindrical coordinates, as we already have done it for the stream function idea, which is the two-dimensional thing. So the two-dimensional form of the cylindrical coordinates is actually called as polar coordinate system. So and then we will use the Java applet to look at those velocity potential functions and their corresponding velocity fields. Okay, let's start with the definition of velocity potential functions. There is a condition called irrotationality, and we already know irrotationality means such a flow field having the curl of the velocity is zero, or verticity vector is zero. This condition of irrotationality in a flow field give rise to some scalar function. We have given a name, velocity potential function, and we can say that this scalar function, if you take the gradient of that scalar function, you will be able to get the velocity field. So mathematically we can say, if we have the condition of irrotationality exists, so that is only true when this condition exists of irrotationality. Then, if this is true, then we can say that the velocity field would be nothing, just the gradient of that scalar function, and that scalar function has been named as velocity potential function. So once you know the velocity field, it means we know the component of the velocity. So the idea of a scalar velocity potential function works only for such flow fields which are irrotational. So if it is not equal to zero, then this would not be true. So as we know that the velocity is, if you take the gradient of that scalar function, so gradient operator is dava by dava x, I direction dava by dava y, dava by dava z. If you take the gradient, actually you are, since phi is a scalar, but if you take the gradient, the resultant is a vector. So velocity is a vector. So phi here is a scalar function. So if you take the gradient of that scalar function, you are going to get a vector, and here the vector is a velocity vector. And if you compare as we know, the velocity, since the velocity is having a u component, and a v component and a w component. Is actually not z but should be a w component. So u, v and w are the components in x, y and z coordinates. So correspondingly we can say that the u component of the, if you compare these two things, so I and I component could be compared, then we can say that u would be equal to dava phi by dava x. So we can simply write u would be dava phi by dava x and v would be dava phi by dava y, and the w component of the velocity would be the dava phi by dava z. So it's so simple. If you have a knowledge of that scalar function phi, so if you differentiate with respect to x, you will get the corresponding velocity component in x, and similarly if you differentiate that scalar function with respect to y, you are going to get the v component of the velocity. Similarly, if you differentiate with respect to z, you get the w component of the velocity. So as you have seen in stream functions, we have restricted ourselves to 2D flows, but here you could have velocity components in x, y and z. So we can say that velocity potential function is a 3-dimensional idea. Okay, so that is, I have talked about, as we know that if the flow field is incompressible, it means the divergence of the velocity is 0. So this, if you see the vector form of the continuity equation, it is actually the continuity equation where you have the divergence of velocity is 0. And if velocity can be expressed, as we already know that if we have expressed velocity in terms of the gradient of that scalar function. So just I have replaced, because, and this is only true, we know that it is only true when the flow field is irrotational. Then we can substitute instead of v, we can substitute the gradient of that scalar function, and if you take the divergence, you are going to get 0, because this thing is only applicable when the flow field is irrotational. So we are already talking about that the curl of the velocity is 0, then the divergence of that velocity would be equal to 0, because that flow field is supposed to satisfy the principle of conservation of mass, which is represented by this divergence of velocity. So divergence of velocity, we have already gone into the physical meaning of the divergence of velocity in the last lecture. So we know once the flux in is same as the flux out, so the divergence of velocity would be 0. Now you can write these two operators, and we call in the differential equation form, we can write it is second order partial differential equation of phi. So when you have an irrotational field and you are substituting into this continuity equation, you end up with this relation, which is a second order, and we know in mathematics which this equation is, this differential equation is called as Laplace's equation. So it's a partial differential equation of second order, and we call that equation to be Laplace's equation, which is nothing just satisfying the continuity and the condition of irrotationality. So we end up with this Laplace's equation, and this second order operator is actually called as Laplacian operator. So phi is a scalar function. If you take the second derivative with respect to the coordinate systems, that would be equal to 0, is a representation that this scalar function is such that it is signifying a field which is irrotational and which is incompressible. So what we end up with, what you call it a potential flow, is such a flow field which is inviscid. Inviscid means their viscous terms are neglected. Incompressible, so it is satisfying the continuity equation and in the manner that the divergence of the velocity is 0, And the third condition for potential flow is that it must be irrotational. So obviously, if condition of irrotationality exists, then obviously we end up with we can relate velocity field in terms of a scalar function. We have given a name velocity potential function, and that would mathematically be governed by a mathematical equation, that is the Laplace's equation, and such a flow field is called as potential flow. So in the beginning I told you that there are two classifications of the fluid flow. One is called inviscid flow, where viscous effects are not dominant, and other is a boundary layer flow, which is where viscous effects are dominant. So in potential flow, viscous effects are not taken into account, and additionally we have to fulfill the condition of irrotationality. If these three conditions exist, then the flow field would be called as such flows are called as potential flows. And practically, if you look at the flow over a certain boundary, let's say you have such a shape having, there is a little bump here, and then the flow straightens out. So if you see the streamlines and the region which is away from the wall, where the condition of irrotationality exists, and we are satisfying the Laplace's equation, then such a flow field is actually called as potential flow, or the flow which is not affected by the viscous effects. If you look closely here after the bump, you see that the vorticities are present. So there is a reverse flow takes place, and so the region in which the condition of irrotationality is not satisfied, and this Laplace's equation is not satisfied, so we cannot treat that flow to be as irrotation. Cannot be irrotational, it is rotational flow, and it could not be called as a potential flow. So secondly, there are regions which are very much close to the wall. We call it a boundary layer region. We will talk about quite in detail in the later part of this course. So that region would be called as a boundary layer region. This region is very much close to the wall. So where the condition of irrotationality is not satisfied. So in those regions, we cannot apply the potential flow theory. So in the fluid mechanics, people divide two regions very distinctively. One region in which the condition of irrotationality is satisfied and Laplace's equation is observed, so we call that flow to be as potential flow, and that would be the flow away from the boundary or having no wakes in it. So such flows are mathematically treated as potential flows, and as we know, if we know these functions, we can easily work out their velocity components now. So the knowledge of the velocity is much easier, and it is more mathematically amenable. You can easily work out mathematically the velocity fields, so in that potential flow regions. But once you go close to the wall, or having some vertices where this condition of irrotationality is not satisfied, then we treat them separately, and we call such flows to be as boundary layer flows. So in boundary layer flows, the condition of having viscosity and irrotationality is not satisfied, and we have to treat them differently. So fluid mechanics problems are usually divided into either it is a potential flow theory or it is a boundary layer theory. And boundary layer theory is obviously the regions which is outside away from the boundary, and having no vertices would be as potential flows, whereas the flows close to the boundary or having backward flows and vortices, such to be treated in this boundary layer flow. So the whole subject of fluid mechanics divided into two regions: potential flow theory and the boundary layer theory. And we will go into the detail about this boundary layer theory after covering this potential flow. As you know from your fluid mechanics 1 knowledge, you have used Bernoulli's equation, which is actually the pressure head, the velocity head, and the altitude heads. So these heads at section 1 and section 2 are balanced because the energy is conserved. So because so far we have not included the friction terms. So it is something like frictionless. So we call it an inviscid flow. We call such flows to be inviscid, and it must be, the density is constant, so it must be incompressible, and there is no point of calculating the velocities or pressure distribution in terms of time. So it is a steady state problem, and obviously we are not dealing with such a cases where streamlines are, so the flow is in the dominantly in the streamline direction. So we are not talking about vortices, we are not talking about flows which are very much close to the wall. So such flows are irrotational. So these are actually the limitations of Bernoulli equations. So whenever you are using Bernoulli's equations, you are talking about actually potential flow, because it is irrotational, it is inviscid, it is incompressible, and obviously there is in Laplace's equation you see the phi is changing with the position, but not changing with the time. So if it is not changing with the time, then it would be additionally called as steady state. So in most of the problems we have solved in fluid mechanics 1 are actually the potential flow problems, and where you are not bothered about velocity changes even at given section 1 or even at given section 2. So you have some average velocity at section 1 and average velocity at section 2 and average pressure at section 1 and some average pressure at section 2. So you are not interested in how at a given cross section the velocity variations are taking place, because the direction of the flow is so-called streamline direction. So where all these conditions are satisfied. So most of the time students make that mistake. They use Bernoulli's equations to evaluate their required parameters without understanding the limitation of that equation. So it is a very popular equation in, especially in fluid mechanics 1 course, and we will use it in fluid mechanics 2 as well, but we should understand that it has its own limitations. So it should not be used for such flows which are compressible or transient or viscous or having condition of irrotationality is if it is not satisfied. So we cannot use in such cases. So we must understand the limitation of this Bernoulli solution. That is actually at that time you were not told that okay, this is actually a potential flow, but now in fluid mechanics 2 you have dealt things more mathematically. So you know that such there are a class of flows which satisfy Laplace's equations and which has certain conditions to be satisfied. So that is something very important. Okay, one more thing which is might you may ask that okay, because as you know, since it is inviscid, so the effect of friction is ignored. But I mean the difference between Bernoulli equation and energy equation is you add some factors for taking care of friction, so head losses. So if you include all these head losses in this Bernoulli's equation, then it can be used for flows having some losses or some energy is lost in overcoming friction. Then that equation would be usually called as energy equation. So right now I didn't have include any head loss term. So if their head losses has been included in the Bernoulli equation, then it is usually called as energy equation. So when you have to get rid of this limitation. Okay, now let's move to the okay, what is essential for potential flow is that this important condition of irrotationality must be satisfied, because vorticity for potential flow is 0, and you know vorticity vector is the curl of the velocity vector, and curl of the velocity vector means the velocity changes are taking place but their net effect is 0, and so the particles are not spinning about their own axis. They are moving, and they are moving with different velocities in the different region of the space, but in a manner that their motion about their own axis is 0, because the vorticity is 0. And we will see more closely when we will go into the vortex flows the idea about vorticity one more time. Okay, so the condition for irrotationality, if we apply it to stream function, let's see, for example, for a potential flow, the vorticity vector must be 0, so the curl of the velocity must be 0. And if we are talking about a 2D flow in which the angular velocity vector, I mean, we can say that the angular velocity vector about z is 0. So if you look at here, this equation is very interesting and important to understand. This is the z component of the vorticity vector in two-dimensional flow. So velocity is changing with respect to y. Velocity of x component of the velocity. Similarly, the y component of the velocity is changing with x, but in such a manner they cancels out, so their net effect is 0. So that is what the condition of irrotationality is. It doesn't mean that the velocities are not changing. If velocities are not changing with the space, then such a flow is actually a uniform flow. But we are not saying that it is uniform flow. But what we are saying is their velocity gradients in y balances out for x component of the velocity balances out with the y component of the velocity with respect to x. So if this balances out, then such a flow is actually irrotational flow. Okay, now let's see my continuity equation. My continuity equation is, what I have done is, in this irrotationality criteria, I have substituted u. What is u here in terms of stream function? Stream function is, if you differentiate with respect to y, for the given stream function, you are going to get the u component of the velocity. So in this condition criteria for irrotationality, I have substituted the value of u in terms of stream function. Similarly, we know that the v component of the velocity can be represented by the negative v component of the velocity is actually how the stream function changes with respect to x. So I have substituted the velocity component v in terms of stream function. Okay, and then we simplify this. So what do you end up with? You end up with another time a differential equation called Laplace's equation. So, but this time it is in terms of stream function, not in terms of velocity potential function phi. So that actually gives us a hint that there is some relationship between psi and phi, because once the condition for a flow field, the condition of irrotationality is satisfied, then the stream function would also be satisfying as a Laplace's equation. So that actually help us to establish a link between psi and phi. So because earlier we have seen that the Laplace's equation in terms of velocity potential function is satisfied, and now we see in terms of stream function is satisfied. So that actually give us a hint that there is a link between psi and phi, and in the next slide we are going to establish that relationship. So we are interested in the relationship between the stream function and the velocity potential function. So if you look here, if the flow field is two-dimensional, why we are calling it two-dimensional? Because the idea of velocity potential function is three-dimensional, but since the idea of stream function is two-dimensional, so we restrict ourselves to 2D problem so that we can compare the relationship between these two types of functions, stream functions and velocity potential functions. So if the flow field is two-dimensional and it is irrotational, it means it has a corresponding velocity potential functions. Then what is true is the streamlines are actually coming from stream function, and velocity potential lines are coming from velocity potential functions, and the physical relationship is that they are orthogonal to each other, means they are mutually perpendicular to each other. Obviously the exception is those stagnation points where the velocity is coming out to be zero. So other than that, you see for example, psi1, psi2, psi3, psi4 are representing stream functions. So these are the corresponding stream functions. So these are the family of lines which are representing the direction of the flow. And there are corresponding lines which are representing by some mathematical function. We have given a name velocity potential function. And at all the time, stream lines and velocity potential lines are perpendicular to each other. So we can say that these two functions are orthogonal functions, and obviously at some point, let's say this is stagnation point, we cannot define stream function, so we actually this orthogonality doesn't exist, but otherwise in the whole flow region the streamlines and velocity potential lines would be orthogonal, and we can see it mathematically as well. For example, as we know, the defining equation for a stream function is that the displacement vector and the velocity vector are parallel. So at a given value of psi, or it means for example, psi is constant for this whole streamline, we call it psi1, and the psi is constant for the whole streamline, we call it psi2. So at a given psi, we have this relationship holds, where because we are dealing with the two-dimensional flow, so we are having the velocity component in x and velocity component in y. If you look at the behavior of the velocity potential function, let's say we have a velocity potential function which is some function of x and y, so some function of space. So we are not talking about unsteady problem, so it's not time variable is not involved here. So mathematically, what if we are interested in the change in the value of the phi would be how the phi changes as you move in x direction times dx, plus how the phi changes with respect to y as you move in the y direction times dy. So mathematically you can write like this. What you know from the definition earlier, that dou phi by dou x is nothing but a u component of velocity. Similarly, dou phi by dou y is nothing, the v component of the velocity. So you have earlier we have an expression of change in the value of the stream function which is representing the volume flow rate. Here we have a change in the value of the velocity potential function, which is this equation. Okay, so let's see more closely this equation. And as you know, when phi is constant at a given value of phi, d phi would be 0 because the derivative of the constant is 0. So this equation on the left hand side comes out to be 0 here. So it is 0, u times dx plus v times dy, and if you simplify this, what you end up with, dy upon dx when phi is constant, it is minus u upon v. As we know early from the definition of constant stream function, v over u. So if you multiply that together, what you end up with, these two gradients, the product of the gradient is equal to minus 1. So that is the mathematical proof of the fact that psi and phi are orthogonal lines, because their gradients, the product of their gradient is equal to minus 1. So that is what we see is, if you have a constant stream function, then there is a corresponding velocity potential function which will be all the time orthogonal to the streamlines. And the idea of flow net is very simple. If you draw the stream functions which is representing streamlines, and velocity potential functions which are orthogonal lines, then you end up with a net called flow net. So dominantly flow is in this direction, so these are streamlines, and the lines which are perpendicular to streamlines will be called as velocity potential lines. And we see it mathematically, we can say the relationship is simple because we have already defined stream function, and we can work out the velocity component u if you differentiate with respect to y. Similarly, if you differentiate stream function with respect to s, you are going to get the negative v component of the velocity in y direction. Similarly, as you know, for mathematical function we have given a name velocity potential function. So in order to get u, you have to differentiate with respect to x. In order to get v, you have to differentiate with respect to y. So if this u is same, it means this thing is same as this thing. And if v is same as this, and this thing would be same as this thing, so we end up with this mathematical relationship. So if you know one of the thing like stream function, you can work out the velocity potential function, and vice versa. Okay, so flow net is nothing, consists of the family of streamlines and the velocity potential lines. Another name for velocity potential lines is equipotential lines. So in the actually that has come from the background of electrical systems, where you have potentials between two lines are same, so we call it equipotential. So voltage is same. So we use it, psi is representing the stream function, and the line perpendicular to would be representing velocity potential functions or equipotential lines. And we know both are orthogonal to each other, and the distance between the two streamlines, for example, this streamline and this streamline, neighboring streamline, delta n is the distance, and let's say the delta s is the distance between two equipotential lines or velocity potential lines. And usually it is a custom that the distances delta s and delta n are usually made identicals, so that we can figure out, I mean, we cannot say the distances are identical. I mean, it is something people always used to write. Okay, if you look at some of those examples, I mean, what we can do is from the flow net, the good thing about flow net is once you're able to draw a flow net, because once you have a knowledge of stream function and velocity potential function, you can plot the family of those lines. So once you plot the family of those lines, you will end up with a figure called flow net. And as you see, let's say just look at this flow over a 90-degree band. So you see the colored lines are actually the streamlines, and the lines which are gray in color, orthogonal lines, are velocity potential lines, or we call it an equipotential lines. So initially the spacing between the two lines is the same. So D and D, everywhere it is, the distance between the two streamlines is same. So we can say that in such cases velocity is the same, because the spacing between them is the same. So velocity is same over this cross section once it enters into the 90-degree band. Okay, as the flow moves over the band, and you can see that close to this radius, the distance is actually d2. I call it d2, position d2 is somewhat smaller than d. And here the distance at one position 1, at the outer radius, we can see the distance is the d1 distance is greater than this original distance d. So we see that at this turn, the distances are different. They are not the same. So once the distances are not the same, it means they are not representing the same velocities. So if the distances are bigger, the velocities are lower, and if the distances are smaller, the velocities are higher. So there is an inverse relationship between the streamline spacing and the velocity. So here particles would move much faster. Here particle would have to travel more distance, so they are a bit slower. And we can figure out that from the spacing we have an idea about where the velocity is higher and the velocity is lower, or velocity is constant. So this is the advantage of having a flow net. And look at this example. We have 90-degree band, but this time a sharp band. So you see streamlines are much closer, so the flow is much speedy. And here at the edge there is a non-uniform distribution. And how we can get rid of this instead of non-uniform distribution? If you make this sharp edge with the curved edge. So by just making a curved edge, you have some better distribution of the velocity. So this is what we usually do. We always avoid those sharp turns, and we have those round turns so that the velocity doesn't change much appreciably. I mean, there is a change, but here it is a much bigger distances between the two streamlines, and then the distances between them decreases sharply. And at the corner there is a very small distance. So secondly, you see that initially you have streamlines much far apart, and then it is much closer. It means, so in this region the velocities are higher compared with that region. Even the mass flow rate is the same, but the velocities are much higher here. Similarly, if it is a reduction, then you can see in this region the flow net represents that, okay, the streamline spacing is much bigger, here the spacing is much smaller, so it means we know that the flow is accelerating at this place. Similarly, what we do is instead of this sharp turn, if you make it a round corner, so we could have a better spacing between the streamlines, and the differences between the velocity can be minimized. If you have such a situation like abrupt jump, so you can see the vertices are there, so where potential flow theory doesn't work, and the same is true in this region close to the wall where potential flow theory doesn't work. And so the distances between the streamlines, and this is something evident in river flows or open channel flows where you could have such a bump, and flow becomes irrotational here. Flow becomes rotational here rather. So the region away from the wall is irrotational, so that we can use the potential flow theory to predict their velocities. We can do the same thing with this polar coordinate system, and in polar coordinate, actually cylindrical coordinate systems, r and theta are the two directions. So velocity in r would be Vr, velocity in the tangential direction to be V theta, which is orthogonal, and velocity is in the cylindrical axis, what we call it a Vz, and we can write the velocity vector, and Er, E theta, Ez are the unit vectors, and Vr, V theta, Vz are the corresponding velocity components in their respective directions. If the flow is irrotational, we know that the gradient of that scalar function would be a vector, which is a velocity vector, and if you take the gradient of that phi, so this would be Vr, this would be V theta, this would be Vz. So we can easily work out the velocity component in cylindrical coordinate systems, and we know that Laplacian equation must be satisfied in two-dimensional, looks like in three-dimensional actually it is, and with respect to z as well. So if you put this cylindrical coordinates in two dimensions, then it will be called as polar coordinate systems, as we already have done in case of stream functions. Now we can do the same thing using this Java applet, and I will show you how we can plot those velocity potential functions. And we take an example of this phi is x squared minus y squared, because if you want to know u is differentiate phi with respect to x, so the derivative would be 2x, and in order to get v differentiate with respect to y, so the derivative would be minus 2y. So this is a velocity field, this is a velocity potential function, and we can see that in the software as well. Okay, so see this Java applet, what I do is here, if I go to the back and I define a user defined potential, and it asks me to define a user defined potential function. So I define it x to the power square minus y to the power square, and just enter here. So I can see, okay, I just see the flat view of that. So I can see that, okay, the field vectors looks like this. So the flow is taking place like this. So here you have, I have the floor I have represented is as a streamline, but I can represent, because the direction of the vector is, streamlines are parallel to the direction of the vector. Whereas in equipotential lines, if we draw, so these are the lines which has been drawn perpendicular to the velocity vector. So perpendicular to the streamline would be called as velocity potential lines or equipotential lines. Here the term is used, equipotential lines. And we can see that in this flow, if we want to see the line integral, because it is irrotational, so the verticity is 0 and the circulation is 0 here. So and even if you see it satisfying the equation for incompressibility, I mean divergence of the velocity vector is 0, so the flux is 0. If you see this surface integral, and this surface integral comes out to be 0 here, and if you see the surface integral here, it's also come out to be 0. So it is such a flow field which is satisfying the condition of irrotationality, as well as it is satisfying the condition for incompressibility. And we can plot such a field just by going into the user defined field, and here I just put it 2 times of x as my x component of the velocity and minus 2 times of y I am going to get. So I got the same field. Like if you see there is streamlines, the streamline looks like the same, and the lines which will be orthogonal would be the same. So actually that represent the same velocity field. So this is how you can practice yourself with those streamlines concept and velocity potential line concepts using this Java applet, and you have a user defined field, you can put your own function. So at this point I stop this lecture. So here we finish today's lecture.